Hi and welcome, ladies and gentlemen. Today we are talking about the shortest path problem again, but this time about the Bellman-Ford algorithm for graphs. Well, the Bellman-Ford algorithm tries to find the shortest path between two vertices in a graph, and it does so by successfully computing the minimal distance between the nodes. And there are certain preconditions and a strong difference to the Dijkstra algorithm. If you didn't see about the Dijkstra algorithm video, have a look here. I blended in for you the Dijkstra algorithm. So the preconditions are that there are negative edges allowed now in the graph. And that is very important because if we have really big graphs, then we don't want to normalize the graphs and all the time, and in the end we have to re-normalize the result again to get the proper distance values if we want to deal in the Dijkstra algorithm with negative edges. So we can use the Bellman-Ford algorithm. That is also a very good algorithm. And there's also another important difference to the Dijkstra algorithm, and that is that cycles are allowed now, just no cycles with negative values. If we have negative cycles, then we have to perform a cycle detection again and remove those negative cycles, or in the end do again a normalization of the graph so that there are no negative cycles anymore. Okay, so let's have a look at an example. Well, here we have the graph given 1, 2, 3, 4, 5 and 6 as the nodes, and we want to find the shortest path between 1 and 6. For the Bellman-Ford algorithm, we have to keep two lists, and that is for each node we have to keep the minimum value, which is the minimum value from node 1 to this node. And we have to keep a list of predecessors with those we will compute in the end the path itself. Alright, so then when we have those initialized, the minimum value with infinity and the predecessor value with none here, then we set the value of the first node to 0. Because from the start point to the start point, the value will always be 0, and that is important because on top of this we want to compute all the other values in the end. So in the next step we have a look at all the edges from node 1. And so we go in and have the 1.5 as a minimum value from node 1 to node 2, that is a weight, and the predecessor will be 1. Then we go to the node 3, and there's a minimum value is 2.7, and the predecessor of 3 will be 1. And then we go to the node 4, and there the value will be 3.5, and the predecessor will be 1. So now we keep going with the 2. The 2 has one outgoing edge, and that is 3.5 to the 3, but the value of 2 is already 1.5 plus 3.5, which is the value of the edge from node 2 to node 3 is 5, and 5 is greater than 2.7, so we don't change anything there. So we keep going with with all the edges from node 3 on, and that is 3 to node 5, and it has a value of 1.1. Plus the value that is currently stored in node 3, and that is 2.7, so we are at 3.8, and the predecessor of node 5 will be 3. And then finally we have the edge from 3 to 6, and this has a weight of 1.5 plus a value in node 3, and that is 2.7, so we have an overall value of 4.2 for the node 6 and a predecessor of 3. Last but not least, we haven't yet computed the edges from node 4, and it has just one edge, and this is from node 4 to node 3. And this is actually a negative edge, and we have a value of -1. And the current value of node 4 is 3.5. 3.5 minus 1 is 2.5 for node 3, and 2.5 is smaller than 2.7 what it had previously. So we set there the value of 2.5 for our node 3, and we set the predecessor of node 3 to 4. So whenever we want to go to node 3 now, we take the cheapest route, and that is from 1 to 4 to 3 with a value of 2.5. Alright, so once we are there, we have to check the outgoing edges from 5 and from 6, but there are no outgoing edges, so we can skip that here. Then we keep going and compute it again from the beginning. So node 1, nothing changed, node 2, nothing changed, node 3 now changed a bit because the value of node 3 changed. So we have there a minimum value of 2.5 now, and we have to recompute the outgoing edges, and that is here for the node 5, this 3.6, because the new value of node 3 is 2.5 plus 1.1 of the edge is 3.6, and the predecessor stays 3. And then we have to do the same for the node 6, where the new value of node 3 is 2.5 plus 1.5, which what it was before. We have a value of 4 now, and the predecessor stays 3. Alright, so we are done with this example. Let's implement it in Python. For that I have a new file here, and I call that Bellman-Ford.python. And for that I want to actually use the graph source code that I was presenting in my graph video. So I blended in here. If you didn't watch it, have a look at it, and you find the source code there. You will also find the source code for all my videos in my GitHub repository. The link is down in the description below. Alright, so now I simply copy here the source code. And the graph algorithm works basically like this, that we have a vertex which stores the index and the name. We use the index for computing the adjacent matrix. Have a look at the video if you didn't watch it. I blended in now the video for the adjacent matrix on graphs. And we have an edge that stores the node from where it comes, so the start node and the end node, node 2, and it stores the weight. So we go in now here and create a new method called Bellman-Ford. So def Bellman-Ford, and that gets the self parameter, it gets the start node name, and it gets the target node name. And these will be actual node names like A, B, C, D, E, and F. Alright, and here I say computes the Bellman-Ford shortest path from start node name to target node name, and I say returns, and it will return the minimum distance from start node name to target node name as well as the path. Alright, so as I said earlier, at first we need the list for the minimum distance, so I call that dist, or let's say distance here, and that will be in the beginning integer or the maximum value that we can store in our variable. And for that I need the system import, so I go up here on my file and say import sys, and we go in here and say that is system max size, and we want it as a list, and the list is actually the amount of elements in our list is the amount of nodes that we have. So lang nodes, and that has to be self.nodes. And we do the same with our predecessors. So here predecessors, but I don't want to give it an integer value here. I want to say none. Alright, what we have to do then is we have to find the index of our start node and the index of our target node, because we will work always on indices. So I say here start idx will be, and there we go in, and now we compute our start idx, and that is x.index, and we go in for x in our self.nodes if, and there we say x.name is equal to start node name. And we do exactly the same with our target index. So target index, and here we have to use target 2. Alright, so now that we have these indices and we have our distances, we can initialize our distance matrix with 0 for our start index. So we can say here init distance at start idx, and there we say distance start idx is equal to 0. And then we want to run n-1 times when n is the amount of nodes we have in our graph, through a loop updating these nodes, because in worst case we need n-1 times to update it. So I go in and say for underscore in range lang nodes -1, and we need here self.nodes. And that gives us basically a loop that is n-1 times long. Alright, so when we are there, I want to say for each edge in self.edges. Now I want to say, to have it a little bit more or a little bit prettier, the algorithm, u is my edge dot start. Or no, I called it node from dot index, and my v is equal to edge dot node 2 dot index, and I say my weight is equal to edge dot weight. And then I go in here and say if the distance, so if distance of u plus the weight is smaller than the distance of v, then I say distance of v is equal to the distance of u plus my weight. And here I have to actually use these brackets, because we access a list there. Alright, and then I have to set here the predecessor of my node v is equal to u. Alright, and then we are already done here with that. So what we have to do now is we have to compute our actual path. So I go in and say path is equal to target idx, and I say our node u is equal to target idx. And then I go in and say while our u is not or while our u is not equal to none. Now let's say here the predecessor of u predecessors, and then I go in here and say path or u is equal to predecessor of u, and I go in and append our u now to our path, so path.insert, and we want to insert it at the beginning. We basically go from the back to the beginning, and just our start node has a predecessor, none. So we go in here and say path.insert at position 0, and we want to insert u. And once we are done with it, we go in and say return our path, and we return our distance of the node target IDX, which will store the length of this of the path. Alright, so now that we are done with it, let us print our graph. Here I want to make or use a little bit different graph than it is written down here. I want to use the graph from our example, and that is actually this one. And then I go in here and say print, so we have there a little bit of some space, and then I say print, and then I want to print g.Bellman-Ford from node A to node F. And when I printed this, we get a little list index in line 76. Here we have to actually use the 0, and here we have to use the 0. And we will get an error. That is fine for this little application if we put in a wrong node name that doesn't exist in our graph. So, and here, as we expected it earlier, we have the node 0, 3, 2, 5 with a weight 4.0 as in our example, just that this list of nodes is indexed by 0, and the list in our example was indexed with 1 or from 1 on. So if we subtract 1 from each node, we have our start node 0 and our end node 5. So we go from 0 to 3 to 2 to 5, and we have a value of 4.0. Alright, ladies and gentlemen, that's it for this video. If you liked it, give it a thumbs up and subscribe to the channel to always get informed whenever I'm uploading new videos. Post down in the comments below what you think about the video. I really appreciate every hint, every comment that you write down. Alright, that's it for me. Have a great day. Bye.